Welcome back to my course. We're talking about algorithm design techniques today, and we have five techniques. We have the brute force, we have decrease and conquer, we have the divide and conquer, the transform and conquer, and the dynamic programming. I will be looking at the brute force in this video. So, brute force. What is the brute force approach? So, the brute force approach is just the straightforward approach to problem solving, the one that is based on the problem statement and the defined concepts primarily. It doesn't really deal with thinking about manipulations of some sort. Oh, I want to transmit the thing, I want to reduce the problem, I want to make the problem look like something. That sounds like a was approach to problem solving. If you're a man, if you're a barbarian or something, you're somebody that is strong, a strong man, you face the enemy head on, like the exams we have on Tuesday. You face it head on, you fight to the death. It won't work in every situation. However, it's the easiest to adopt, and it challenges problem head on. And our examples we have the selection sort and bubble sort. So it's just these are basically sorting algorithms, and these do the same thing but in two different ways. For the selection sort, it works with minimum values, and this works with maximum values. How do they work? These guys, we'll look at them one after the other. So selection sort, don't let this all scare you. What's going on here? It scans the entire list to find the smallest element and then swaps that with the first. So it's minimum and it swaps to the first, while the bubble is maximum values and swaps to the last. But still on selection sort, it's just about scanning an entire list to find the smallest element and swapping it to the first position. But that's not all. It will have to scan again and again and again till um till everything has been sorted. And the way it does it is after it searches for the smallest element and puts that at the first position, this position becomes indisputable. You can't fight for that position anymore. So it removes that from the range of operations. So the next thing is start searching from the index after that to the end, and then it will find the smallest and swap that to position 2, which will also become indisputable. Then you start from position 3 to the end, and if it finds the smallest, swaps that into position 3, which becomes indisputable all the way until position n minus 1. So at that point in time, there will be no further key comparisons, and then we can call it a day with that. So if you look at this illustration, it shows clearly these guys have been done, and you see they're on the left hand side from the beginning to the position I minus 1. So all of these are in order now. But then if you look at this, we have AI, which is the current position, and then it finds a minimum value, a min, on its way to an minus 1. So what it does, it swaps that to the new position of AI, which then becomes indisputable. Then the bar shifts such that we are now starting from AI plus 1 down to, and then when we find the minimum, we swap again all the way until we get to the end where there's no more that can be done. So if we look at the algorithm, we see here that the selection sort takes in an algorithm of index 0 to n minus 1. It will sort it in the selection sort manner, and it would output the array, but in non-decreasing order. So it will be in ascending order, it will return it. So how does the loop work? So when for I is equal to 0, n all the way to n minus 2, not n minus 1, and I'm going to explain why. Then initializes the minimum value, which is I. That means in the case where it is 0, it's I, blah blah blah. And then for j is now I plus 1 to n minus 1. So it will not start comparing. It will not start comparing from I, which has been selected as the minimum. It will, let's say we have 0, 5, 7, 8, 9. I has been selected here. It won't start comparing from I. It will start comparing from these guys all the way to these guys. So if it finds another smallest or the smallest element, then it swap that to this place, and then moves on, and then starts trying to fill in for the second position, and so on and so forth. So we know that this AI is the beginning, the I is the beginning, and then this one is dealing with all right, so the start position is not going to be on I, it will be on the thing after I, the element after I, all through to n minus 1. So for every one loop of this outer loop, this one will loop through completely. I'll say it again. For every instance, every iteration of this one, if this one iterates once, this one will iterate from beginning to the end. So this will go from 1 to end for every one of this. So on 2, it go from that whatever it is to end. So like now, if we look at it, we know that the starting position of j is from the increment of I. So if I is 0, j will go from 1 to n minus 1. And if I is 1, it go from 2 to n minus 1. And then if you notice, 0, I must not go beyond n minus 2. So if I is n minus 2, then j will be n minus 2 plus 1, which is n minus 1. So at that point in time, there'll be nothing else to do. So I will basically not even do a comparison at that point. It will just stop. So having said that, this is now the meat of this is the basic operation here, where aj is less than a min. We swap the mean value to j and then replace ai with it, this guy here. So it will be changing like that. It will be changing like that, swapping out, swapping out, swapping up, until all of the values are sorted from minimum to maximum. All right, so we'll look at an example to deal with that. So let's say we start here. We have this, so we're starting with this. So this is I naught, a naught, a0, a at index 0. It will start checking from this guy I plus 1 all the way to n minus 1, which is the last guy here. So 85, is it less than 45? No. Is it less than, well, yes, it is. But then when it does that, then the next, it will loop again. Is 45 less than 68? No. Is 45 less than 90? Then it will do that all the way. Is all the way. It's actually 89 is being looped through to check on this, all of these guys. It's not replacing. So 89 will check for 45. It's less than it, but okay, it will still keep on iterating. 89 is less than 68. Fine. 89 is not less than 90. Fine. Check 29. Oh, it's less than. We check. So it will be checking. It will be checking, and then whatever it will be replacing actually. It will put 45. It will not put anything. It will put 29. It will not put 34. Then when it finds 17, it will put 17 in. This guy will now be the true smallest value, and then that will be shifted. So the next thing you'll find is 17. Then 89 will leave where it was and go to that side. So 45, 68, 90, 29, 34, 17. Let me go over the operation again. This is I is equal to 0. So it starts from I is equal to 1 all the way. And then as it's finding the values that are smaller than it, it will be replacing until it finds the smallest and won't replace anymore. So what it will do is swap that out and then to move on and start from here all the way to stuff. At this point in time, this one won't change anymore because, oh, did I put 17? That should be 89. That should be 89. So at this point, nothing is going to challenge this anymore. But then it will go from this all the way to this. So the next thing, 45 is not less than, is less than 68. Fine. It's less than 90. Fine. It's not less than 29. So this guy becomes the smallest value. If you check again for this, that's not working. Check again for this, that's not working. So the next smallest value is 29. So we have 17, then 29, then the bar showing that these are permanent. Then since it's swap 45 to 29, we'll have 68, 90, 45, 34, and 89. Then we check from 68. Is 68 less than 90? Yes. 68 is 45 less than 68. Yes. We swap, but then we still check, is now 45 now less than 34? Yes. So we swap again. So 34, is 34 less than 89? No. So the next smallest value is 29, then 34, and then we lock in. So since we swap 68 with 34, we have 90, 45, 68, and 89. So 90 is the smallest value here. Is it less than 45? Yes. Is 45 less than 68? Yes. No. Is 45 less than 90? Yes. Is 68 less than 45? No. Is 89 less than 45, no. So we swap that in, so we have 17, 29, 34, and 45. If we swap 45 and 90, we'll have 90 still, and then 68, then 89. Should make more space. It gets, your tongue starts twisting after a while, and you start confusing with all of these long lists of stuff to do. We have this, so these guys are not touched anymore. What we are touching now is these guys. So 90, we're going against these two. Is 68 less than 90? Yes. Is 89 less than 68? No. So 17, 29, 34, 45, 68, then lock in 90, 89. Last comparison. Is 89 less than 90? Yes. So we swap again, so we have 17, 29, 34, 45, 68, 89, and 90. And then we have that already set out, and we've sorted that out. So that is the sorting that will go on. We'll then look at the analysis of this, the plan and analysis of it. So let's start with number one. Plan was that we want to know whether the input size is n, or there are other things that are affecting the input size. And then if we look at this, it's going from I to n minus 2 and everything, and then it's ending n minus 1. It's basically just observing everything. There's no special time where it is only doing small things. It's going through everything. It's a traversal algorithm. Actually, it will traverse through everything. So the input size is n. Input size is n, and n is the total number of elements. So the next thing is to check for the basic operation. What's the basic operation here? The basic operation is going to be this guy, because it's the one that will happen the most. It's also inside the for loop. It's the one that is responsible for all of this checking, and swapping that's going through. So if aj is less than a min, that's going to be, so basic operation, if aj is less than a min. Now, if we check for number 3, do we need to do best case, worst case in this case? It's doing for everything. It's doing for everything. So there's no best case, there's no fair weather, there's no good chance of something, there's no bad luck. It's going to do for everything. So all we are need to worry about is the count. So no need for best, AVG, and worst case. So number 4, we're just trying to get now the sum formation out. So what is it going to look like? And that's for the count, right? So the count we now have, okay, what are we doing? We are going to have to deal with both of the for loops. So we have to deal with this for loop and this for loop. So what we will be having? We'll be having the for loops. The first summation will be from I is equal to 0 to n minus 2. The next summation, this guy will be from n minus 1 and from I plus 1 to n minus 1. And then this happens repeatedly once within this loop. To happen repeatedly once from this point to this point. Once. So we'll have 1 here. This guy will be happening once from beginning to the end of this. While only one iteration of this will happen, all of this will happen. So let's now just write that out. So what will the summation be? We'll have two summations from I is equal to 0 to n minus 2 and j is equal to I plus 1 n minus 1, and then we have 1. Remember our formulas where you have u minus I plus 1, where u is this guy and I is j is this guy, and then plus 1. Imputing that into this, we have the previous sum from n minus 2, I is equal to 0. Putting that, we have n minus 1 minus I plus 1 plus 1. If we open this, we'll have n minus 1 minus I. So the new sum form will now be summation of n minus 2, I is equal to 0, n minus 1 minus I. So when when I is 0, you have n minus 1. When I is 1, since it's summation, you have n minus 1 minus 2. When I is 3, when I is 2, you have n minus 3. When I is 3, you have n minus 4, all the way till you have n minus 2, n minus 2, then plus 1, since we are taking this, and then we are checking for everything. So n minus 2 plus 1, so we have the ends will cancel themselves out. So uh, n minus is supposed to be, so it's basically supposed to give you n. Oh, it's not supposed to be in bracket like that. I'm sorry. We have n minus, since we are doing 2 3, and then it's I, we just put n minus 2 in the place of I, so we have 1 minus, so minus 2 minus I, right? So what do we have? Minus 2, minus 2. So these guys will cancel themselves out. We have a plus actually when we open the bracket. Why did I get so confused there? So we'll have, when we open the bracket, we have n minus 2 minus this bracket, so n minus 1 minus n plus 2, right? That's what we're supposed to have. Pardon me for that. So we'll have the n cancelling out, minus 1 plus 2 will have 1 eventually. So if you consider everything that just happened, pardon my math, it's bad. I'm just getting tired. Okay. So we have this. What then do we have? We will see that this is more like a regression, like from n minus 1 all the way back to 1. So if we invert that, you see it looks like 1 all the way to n minus 1. So the summation of this is going to give us n minus 1 divided by 2. This is the summation of all of this that we just did. All of this equals all of this, and that equals to this. So this, if we decide to open the bracket, we'll have half n squared minus half n, and then we can discard all of this because we want to deal with the highest derivative. So we'll have approximately half n squared, and in that case we know that that is a member of the big theta of n squared. So we know the complexity now, and we know the order of growth is in the degree of polynomial the degree 2. Yes, polynomial degree 2. So this is the analysis for selection sort. Pardon me for I'm a little sluggish today. So that's all about selection sort. We've looked at the algorithm, how it works. We've also looked at an example, and we've also looked at the analysis of it. We know that the basic operation is this guy. We know that when we run in the entire summation forms, we are going to end up having a polynomial of degree 2, and that will be the order of growth. Now moving on to bubble sort. Bubble sort is basically another brute force approach. Excuse me. Okay, so we are comparing the adjacent elements, the elements that are right beside each other, and exchanging them if they are out of order. Let's say we have 5 and 6, and we have 6 and 5, and we are going to swap them such that they are non-decreasing order. We are going to have to swap 5 with 6, and then we'll do that repeatedly until the largest value gets to the other end, the right end of the list. I'm going to explain with an example. So we are trying to just bubble up the largest value to the end of the list. We don't want the big values to be at the middle or at the beginning. The big value should be at the end. For selection sort, we went from small to big. We were like searching for small values and adding them like this. For bubble sort, we are bubbling up the big values until they end up at this side. The small values, we're adding them like this, for selection sort. We're adding the small values like this. But for the bubble sort, we are adding the big values, going like this all the way. to the end. So that's just the structural differences between the bubble sort and the selection sort. That's the difference between the bubble sort and the selection sort. But then let's just look at how that works. So here is a pass I. So that means maybe pass 7 it has done 7 comparisons, or 8 comparisons. It goes from a of a naught or a of index 0 all the way to the pass j. Then it will check for j and j plus 1. If j plus 1 is less than j, it's going to swap these guys like this, such that the bigger guy is now here, and then to keep on doing that with each pass until all of them arrive at this point, where this is their undisputed spot, where they are already arranged in an orderly fashion. So it's by just basically shifting the largest values until they end up at this side of the list. That's what's going on. So let's look at an algorithm to do that. We have the algorithm that has an index of 0 to n minus 1. It sorts an array using bubble sort, yeah, and then the input takes that. You know, the output is an array in a non-decreasing order, the exact same result we want from the selection sort. Now look at the arrays, how the array is structured. It goes from I naught all the way to n minus 2, and then j is equal to 0 to n minus 2 minus I, which means that after when I iterates at 0, it will check for everything. When I has reached 1, it means that at that point in time, there's already a largest value. So you see that it's n minus 2 minus I. So it's going to be at the other end. It's going to be at this point. If we are going all the way to this point, it starts blocking variables at this point. So at this point, it starts cutting it off. So if I is 0, n minus 2. If I is 1, n minus 3. Okay, so n minus 1, because it's going to do plus 1 here. So n minus 1, n minus 2, n minus 3. It blocks again at n minus 4. It blocks again at n minus 5. It blocks again at n minus 6. When I'm saying blocks again, it means that at this point in time, all the largest values have been appearing and they're already ordered here. So we're no longer doing comparisons on this side of this. We are doing comparison for all the unordered somethings on this end. So as they are getting ordered, they are being blocked, 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 blocked until there is no more somethings that are being. You see that that's how the structure looks like. Having said that, back to the algorithm structure. So it goes from I is equal to 0 to n minus 2. This goes from j is equal to 0 to n minus 2 minus I, and then this goes a little bit further. We are stopping at n minus 2 here because within the innermost loop there's something that is going to go a step further from n minus 2. So n minus 2 plus 1 is what? N minus 1. N minus 1 is the final index of the array. If we say this is going to n minus 1 instead, what will happen is that this would be going all the way to n minus 1 plus 1. So n minus 1 plus 1 is n, and that doesn't exist in this array, so it will be out of bound. That's why we have that, and then we have the innermost loop having this and then a swap. So what are we swapping? If the next value after j is less than j, if the next value, that's j plus 1, that's the index j plus 1, if it's less than index j, we're going to swap. So if for instance we are saying that index j is going to be like maybe 9, and then index j plus 1 is now 6. Since j plus 1 is less than this, we are going to have to swap. So we are now going to swap that, so it will be 6 and 9. And since it's going to keep doing all the iterations till n minus I, it's going to keep on swapping anything like that that is bigger until it gets to the end of that stuff, which in this case will be n minus 2. For 0, it will be n minus 2, then n minus 2 and n minus 1 is what's going to be checked. So that is that. We will then now look at an example so that it doesn't look like I'm crazy. So what do we have? We have these guys, and then we want to sort them. another. How many elements is it? 1, 2, 3, 4, 5, 6, 7. So at the start, we have 89, 45, 68, 90, 29, 34, and 17. This guy will be considered at the beginning in J. So this is J, this is J plus 1. So is AJ plus 1, is AJ plus 1 less than AJ? Yes, AJ plus 1 is less than AJ. Because of that, we are going to swap. Right, so when we swap, we have 45, 89, 68, 90, 29, 34, 17. This is J now. This is J plus 1. Is J plus 1 less than um, less than J? Yes. So we are going to have to swap again. So 45, 68, 89, 90, 29, 34, 17. This is J. This is J plus 1. Is J plus 1 less than J? No. So this guy, we'll move on to J plus 1. We'll just skip that. So now J plus 1 here will now be our new J. So this J, is this J less than this J? Is this J plus 1? This becomes the new J plus 1. This is now our current J. So the new J plus 1, is it less than the current J? Yes. So we swap again. So we have 45, 68, 89, 29, 90, 34, and 17. So now this is the new J. This is J plus 1. Is J plus 1 less than J? Yes. So we swap again. 45, 68, 89, 29, 34, 90, and 17. Now, is this is the new J? Is this J plus 1 less than the J? Yes. So we swap one more time. 45, 68, 89, 29, 34, 17, and 90. And this is the final position. Since we've searched through everything, we know that there's nothing bigger than 90 anymore. So we can call this our first pass. First pass. Now, going through again, we just write out what we now currently have: 45, 68, 89, 24, 34, 29, yes, 34, 17, then 90 is safe. So we check from here. Is J plus 1 less than J? No. So now we move on to the new J, because this is now our current J. Now, is this J less than this J plus 1? Is J plus 1 less than J? That's the question. Is J plus 1 less than J? No. We shift, just continue now. So this will now be the new J. So is this J plus 1 less than this J? Yes. So 45, 68, 89, sorry, 20, 29, 89, 34, 17, and 90. Next question. Is this J plus 1 less than J? Yes. So 45, 68, 29, 34, 89, and 17, then we have 90. So is the J plus 1 less than J? Yes. So swap one more time: 45, 68, 29, 34, 17, then we have 89 and 90. This is the second pass. Now, moving on to the third pass, we now have write it out again. We have 45, 68, 29, 34, 17, and then we have 89 and 90 undisputed. So check 45. Is 68 less than 45? No. This becomes our new J now. Is 29 less than 68? Yes. So 45, 29, 68, 34, 17, 89, and 90. So we check again. Is the new J is J plus 1 less than the new J? Yes. So swap again. 29, 34, 68, 17, 89, and 90. Alright. So we look through again. You see that the J plus 1 is less than J. So swap again. 45, 29, 34, 17. Then we have 68, 89, and 90. Undisputed. Third pass. So we look at what we've got left: 45, 29, 34, 17, 98, 9, and 90. And then when we consider is 29 less than 45, yes, so we swap. So we have 29, we have 29, 45, 34, 17, 68, 89, 90. And if you look at this, is j plus 1 less than j? Yes. So we have 29, 34, 45, 17, 68, 89, 90. Now, is j plus 1 less than j? Yes. So we have 29, 34, 17. Then the new values, say 45, 68, 89, and 90. Let me just crop all of these and make them smaller. Okay, so this is the fourth pass. What then do we have to do with? We have these guys now. So 29, 34, 17, 5 all the way to 90. Now, is j plus 1 less than j? No. Then this becomes our new j. So is j is j plus 1 less than this? Yes. So we have 29, 17. Then we are safe again. 34, 45, 58, 89, and 90. Now we have that as our fifth pass. Then finally we now compare 29 and 17. All of these guys are there. Is j plus 1 less than 29? Yes. So 17 comes forward, 29 goes backward. And then at that point you can say that we've had our final pass. 5, 68, 89, and 90. And this is our sixth pass. So if you notice, there was 7 items, but then there were 6 passes. So there was n minus 1 passes. So start from n minus 1, n minus 2, n minus 3, all the way to 1. Now, having said that, we can now look at our analysis. So back here, we know that this is the stuff. What is the input size? As according to general plan, we have to start with number 1, determining the input size. The input size should be the entire element of the array, because there is no search key or any factor that is controlling the input size apart from the arrays that. So what do? We write number 1, input size is n, total elements in array. Question 2, what is the basic operation? Checking this guy, what do we see? The basic operation would be this guy. The key comparison for a sorting algorithm is usually the basic operation, and it's happening in the innermost loop. Though we have a swap, but this guy is not as valuable as this guy over here, because it's the one that does it. It is the one responsible for everything that is going on. So what we write, the basic operation is if a j plus 1 is less than j. So the basic operation is if a j plus 1 is less than a j. So that's the basic operation. Number 3, do we need best case, worst case, anything like that? No. All we need is the count. Why? Because there's no specific scenario that causes us to have a best case, average case, or worst case scenario. Everything goes the same way. It will be the same for whatever we are trying to do at all. So what would that be? There'll be no need for best, average, and worst case. Then moving on to 4, we need to check for the count of the basic operation. So how do we do that? Let's check the for loops. So we know that there is a summation here from I is equal to 0 to n minus 2. The next summation is j is equal to 0, n minus 2 minus I. So since they are nested, it will form this way. It will be I is equal to 0, n minus 2. Then another, since it's nested, we have now this. So it's a sum of a sum. So there's an inner sum and there's an outer sum, but let's not get ourselves confused with that. And then what is happening here? One comparison happening each time within this particular for loop. Then all of these is now happening each time in this particular for loop. So when the outermost loop loops once, the innermost loops one to the end. If you loop on the second one, it goes one to the end again. Goes to the third one to the end again. That's how it does. So there's an entire sum going on inside for all these four sums. So the total of this will now be the sum of this guy, while the total of these is the sum of this guy. I hope you understand that. Having said that, let's apply that to our count. So what do we have? We will now have, so we have this guy, I is equal to 0, n minus 2. And we have j is equal to 0, n minus 2 minus I, and 1. Remember our formula, u minus I plus 1, where u is this and I is this, plus 1. So what did we say that would be? Let's just put that into this. Then we have n minus 2, I is equal to 0. Then we have n minus 2 minus I plus 1, because 0 is not doing anything. So what do we now have? We then have summation of n minus 2, I is equal to 0, n minus 1 plus, minus I. This is what I'm going to be left with. And remember what we did in the last time, where if we expand this summation from 0 to n minus 2, we have n minus 1 plus n minus, when I is 1, n minus 2 plus, when I is 2, n minus 3 plus all the way to when we have this top value, which is n minus 2, right? So if we have that, then we have a minus 1, right? So if we have that, we have n minus 1 plus n minus 2 plus n minus 3 dot 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 dot. When you expand this, n minus this minus opening the bracket will be n minus n, which will cross these guys out. The minus will affect the minus here and make it plus. So 2 minus 1, which is 1, plus 1. So because of this increasing all the way to this, the sum form will be n minus 1 over 2. And then if we expand this further, we have approximately half n square, which is an element of the big theta of n squared. So we have already determined the order of growth, and we know we have analyzed for the bubble sort. We've analyzed for the selection sort and for the bubble sort, and we have come to the end of this particular class. So thanks for watching. I'll see you in the next video.